Today, we're going to take a deeper dive into electric current, short circuits, and open circuits, and we're going to do it by building practical circuits on the bench. We'll use Ohm's law to calculate the current in a circuit, and we'll take a deeper dive into the factors that govern electric current. We'll wrap up by building simple circuits that demonstrate what an open circuit and a short circuit is and talk about the dangers of short circuits. Voltage, current, and resistance. So we're going to zoom in and talk about current here to have a really good understanding of what that means. So ignore this at the top for just a second and go back down memory lane with me where we discuss voltage, current, resistance. Voltage is the push in an electric circuit. Nothing is flowing when we talk about voltage. It's literally the push. The voltage would be like standing on the top of a mountain. However tall the mountain is, the more potential there is, if you throw a rock off, for it to accelerate down and do some work as it impacts the ground and slams into the ground. But the actual flowing elements in a circuit are the electrons, and that current is associated with how many electrons per second are actually flowing. And we're going to talk in detail about this definition of current in just a second. So voltage pushes or provides the push for the electrons which are doing the flowing, and anytime something is flowing, it's flowing through a resistance which tends to lower the value of the current. So in terms of units, voltage is volts, current is amps for A for amps, and resistance is ohms. We use omega. Now those are the basic units, but we can of course modify those units. If we're talking about thousands of amps of current, we would use kiloamps, so we put a K in front of it for kiloamps. If we're talking about thousandths, 1/1000th of an amp, we would use milliamp. We might use microamp for 1/1,000,000th of an amp. We might use nanoamps or picoamps. You can put any metric prefix in front of these as you might do so for meters or liters or whatever, but the base unit is amps. And same thing with voltage. We deal with volts, but we might think about millivolts or microvolts or kilovolts. Same thing for ohms. The base unit is ohms, but we might talk about milliohms, kiloohms for thousands of ohms, mega ohms for millions of ohms. So current is what is actually flowing. It would be like water moving down a stream. The volume of water flowing is going to be the electric current in terms of the analogy. Now, all three of these are wrapped up into the famous Ohm's law. These are two different ways of writing the same thing. If you take this form here, V equals IR, the voltage is here, the current is here, the symbol for current is I, and the R is the resistance. So the voltage across any circuit element is equal to the current flowing through the element times the element's resistance. Now this is algebra, so I can solve this thing for I, divide both sides by R, and I'll get an equivalent form. The current is equal to V over R. Now these are things that we've talked about in the past. We're now zooming in a little bit deeper into the concept of current, electric current. We want to understand what factors influence the current. In terms of the physics of the wire, when do you get higher current versus lower current? We also want to talk about the concept of a short circuit and an open circuit because those come up extremely frequently in circuit analysis. All right, to get started, here's my light bulb. I'm going to move that out of the way. We don't need the light bulb right now. We have a single resistor, and this resistor is a physically large resistor. It's large like this. Most resistors are physically small. This is a large one because it can take more power without burning out. So I use a large one so I don't have to worry about the thing burning out. What I'm going to do is connect a voltage source across this resistor, and I'm going to draw a circuit for you in just a second so we can see what it looks like. But essentially there's nothing else in this circuit other than a 10 ohm resistor. You can see it printed right here. Of course, it also says 10 watts because it can take 10 watts of power before it burns up. Most of these little bitty resistors you see on circuit boards are usually a quarter of a watt or maybe a half a watt, so they cannot handle as much power. Here, I'm going to run quite a bit of current through it, so I don't want to burn anything up. So what I want to do first is I'm going to run a known current through it, and I'm going to run 5 volts through it. We're going to do a few little examples here of 5 volts. Just going to get some practice with Ohm's law and also with short circuits and open circuits. So I got to start somewhere. So what I'm going to do is dial in my supply. It's hard to get it exactly, this particular supply, to exactly 5.00 volts. So I'm going to leave it here at 5.01 volts, and I want you to notice that the current that this supply says it is power that is sending, the electric current sending through this resistor, 0.496 amps. Also down below, this is how many watts of power is being supplied by the power supply as well. So 0.496. So what I want to do is turn it off for just a second. Let's draw the circuit for this and label where the current is going, and then we're going to talk in a little more detail exactly what this number means. It was about 0.5 amps of current. We want to understand what does that actually mean in terms of charges flowing. We want to understand what that actually means. So what we'll do is we'll draw a very, very simple circuit. So we have a 5-volt source. You can represent this with a circle and a plus minus inside of it here. And we can label this as 5 volts. I could use any voltage source I want, but I chose to use 5 volts because it's a nice number for this. And I have a 10 ohm resistor. So the symbol for resistor is this jagged line. And there was nothing else in the circuit. So we go and close the circuit back around to the source. Now, these are the wires here. In reality, the wire, the actual copper wire on the bench here has a tiny amount of resistance also, but we ignore it in circuits. We say that the resistance of the wire is so small we don't care about it, so we're pretending that these lines here have no resistance at all, and this is the only resistor in the circuit, and this resistor was 10 ohms. All right, so we're going to talk a whole lot more about current in a second, but the way we're going to label our diagram is we know that the actual electrons come out of the negative terminal. If you go over here to this power supply, it's hard to see with everything plugged in here. I guess I can just unplug one of them real quick so you can sort of see. Maybe you can see, there's a minus sign underneath and there's actually a plus sign under the red side here. Okay, what that means is that the plus side, it's telling you the voltage with respect to the other terminal, the minus side. So this means the red wire is 5 volts higher when I had it dialed to 5 volts higher in potential than the black wire. If you think about a battery, you have the bottom and you have the top. And I told you in the last lesson, the battery was like a mountain. The top of the battery is like at the top of the mountain with the potential to do work, sending the electrons out. When the electrons get back to the other side, they don't have any more potential energy left because they've gone down the mountain. Same thing here at the red terminal, you're at the top of the mountain. And as you go through the circuit and kind of go back around, you're falling down in potential. When you get down to this terminal, you have no more potential energy left. Then it goes back into the supply and the process starts over again. But in the real world with real wires, the actual electrons are the elements that are actually flowing, and they're flowing out of the negative terminal. So if we go over here to the black wire, physically what's happening is electrons are going through this black wire, through the resistor, through the red wire, and then back in again, and then they continue to be accelerated around and around again. They come out of the black wire. But in electrical engineering, we don't usually talk about electron flow because electrons have a negative sign and it puts negative signs in your equation. So actually, instead of a negative charge flowing this way, we talk about an imaginary, fictitious, positive charge flowing out of the positive terminal, right? So yes, it's true that electrons are doing the flowing. They're called the charge carrier, right, in wires. The reason the electrons are the charge carrier in wires is because things like copper and gold and other conductors, they have a lot of electrons surrounding the atom in what we call the valence shell. Very, very loosely bound, almost free electrons. It's almost like copper has a sea of very weakly bound electrons, and it's easy to get them moving. That's why copper can conduct electricity. But something like this plastic pen does not have a lot of electrons in the outer valence shell there, so it's harder to get them moving, and so this thing does not conduct electricity very well. But what we say is that even though the electrons are doing the moving, they're negative and they're going this way. That's the same thing as a fictitious positive charge going the other direction. This is called the whole current. I'll put this here, whole current. And if you don't like this, or if you don't understand it, that's okay. I'm going to draw a much better picture of the whole current in a few minutes. But just note that on circuit diagrams, when we have the positive terminal of the source, we always talk about positive current going out, but in the back of our mind, we know it's the same as the opposite charge being negative flowing the opposite direction. All right, so this is the simplest circuit that we have, and we know that we have Ohm's law, You can write it like this, or you can write it like this. So we're going to write down that the current flowing in this circuit is equal to V over R. But in this circuit, the voltage was 5 volts, so I'll put 5 volts there, and the resistance was 10 ohms. Now I'm working in the base units of volts and ohms. I always recommend, like if you had milliamps or microamps in your circuit, or kilo ohms or mega ohms, just convert everything to the base unit of volts and ohms, and then do your calculation. And if you want to move to a different metric prefix at the end, that's fine, but do your calculation in terms of volts, ohms, and amperes. And that way you're always in the base unit. So I'm in volts and ohms, and that's 5 over 10, which you all know is 1/2. And so the current flowing in the circuit should be 1/2, or 0.5. What unit? Well, we already said volts base unit is, the voltage is in volts, the ohms, the base unit is omega in ohms, and so amperes is going to be the base unit, so amps. And that's exactly what we saw. When we dial this thing, when we turn it up, we see the current going up in lockstep with the voltage, right? And when I get over here to 5, as close as I can get to 5 without really overshooting it, it's not going to be perfect, then I get 0.496. Why isn't it exactly at 0.5? Well, it's not exactly at 0.5 because this power supply is not exact. This resistor, even though it says 10 ohms, is actually not exact. It might be a little bit more or a little bit less than 10 ohms. The wire here has very small resistance. And other factors as well. So it's never going to be exact, but it's close enough that we know that what we have put on the board, it represents reality, and Ohm's law is validated and verified. So let me ask you a question. If I were to change this resistance, what would happen to the circuit? Well, the voltage is set at 5.01. That would be the same. But if I change the resistance, it would be like changing this number here, and the electric current flowing would change in accordance with Ohm's law. So here, I have a 50 ohm resistor. That means, so here what's currently flowing is 10, or what's in the circuit is 10 ohms. If I swap it out, I'll just disconnect it here, and I'll swap it out for a resistor that's 5 times larger. Do you think the current is going to go up or down? This is part of this practical part of this class. I want you to predict ahead of time what you think will happen. If the resistance goes up, the current's going to go down. Because why? If the resistance goes up, you're dividing by a bigger number, the current goes down. The resistance attempts to limit the amount or lower the amount of electric current. It's literally an impediment or a resistance to the flow of those electrons in the circuit. How much? Well, the original circuit was 10 ohms. This one is 5 times larger resistance. That means I expect that the current should be 5 times smaller if I connect it. So what I'm going to do is connect this side right here, connect this side right here, and let's see what we get. So instead of 0.5, we get 0.1, which is exactly 5 times smaller. Just to compare it, let's go down here and compare it. Here is the 10 ohm resistor, and we get half an amp, 0.5. Now we change this to a resistor 5 times bigger, so the current should go 5 times smaller. And instead of 0.5, we get 0.1, which indeed is 5 times smaller. Now let's go over here and just verify it with Ohm's law. If I change this from 10 ohms to 50 ohms, then it's going to be V over R, and the voltage would stay the same at 5 volts. The resistance, I changed it from 10 to 50 ohms, and 5 divided by 50 is going to be 1/10, right? Let's just simplify the fraction. And the unit here is going to be amps, and 1/10 is 0.1 amps. And this is exactly what we get. So I want you to get a practical feel for what happens when you change the resistance. Should the current go up or down? And how much should it go up or down? Okay, now to round it out, I'm going to disconnect this guy. So it was 0.1 amps, and I'm going to change it to a 100 ohm resistor. And if I go from 50 ohms to 100 ohms, I'm doubling the resistance again from the 50 ohms. So when I had the 50 ohms in place, I had 0.1 amps. What do you think will happen if I double the resistance? If I double the resistance, I should take the current and cut it in half. So going from 0.1 amps, 0.05 amps. And to see that mathematically, if I go over here, I change this again to now 100. I is V over R. The voltage is still 5 volts. The resistance, I changed it to 100 ohms, right? And so 5 divided by 100, you just move the decimal 2 positions, 0.05, and the unit is amps, 0.05 amps, and that's exactly what I get on the display. Of course, it's not exact because of the reasons I taught you just a minute ago. All right, so as we change the resistance, the current changes in accordance with Ohm's law, exactly in lockstep with the change in the resistance. Resistance goes up, current goes down, and so on. Now, before I go any farther, I want to disconnect this over here, and I want to show you that these values of these resistances are not exact. All resistors have a tolerance to them, and that means they cannot make them exact. These are not super precision numbers here. These numbers that are printed on these resistors, they're not exact. So what I'll do is I will change my meter over here to ohm. So I'm going to measure the resistance over here, and then we'll start off by measuring this. This is supposed to be a 100 ohm resistor. So I'll do a nice little contact point and a nice little contact point, push really hard. And what do I get? Do I get 100 ohms? No, I get 98.9 ohms. But keep in mind that as I'm pushing on it here at the contact point with the probes and the wire, there is a small resistance there. The more I push, the better it is. If I just push a little bit, you can see it's going to read 99. Well, that's actually pretty good. But if I just push just a tiny bit, it's going to jump around. It's not going to be very accurate. But if I push hard and get a very low contact resistance or high contact pressure, and I can see it's not 100, it's 98.9. Okay, what about this one right here? This reads 50 ohms, but actually what is it going to be? Not 50 ohms. It's going to be a little bit bigger or a little bit smaller. In this case, a little bit larger, 50.6 ohms. So it's not always bigger or smaller. It can go either way, and you don't really know until you measure it. This is 10 ohms, and of course it's not 10 ohms. It is a little bit more at 10.2 ohms. All right, now here's the other little wrinkle here. Right? I'm teaching you that these resistors are constant values. These resistors are constant, right? They don't change. In reality, everything changes, right? And so as these resistors heat up, the resistance changes a tiny bit. Same thing with light bulbs. As the light bulb gets hot, physically hot, the resistance value can change a little bit. So, but we ignore that and we say that these resistor values are constant unless you're just trying to do something extremely precise, you have very accurate measurements or something you have to do. We just assume that everything is constant here. Now what we'd like to do, just to learn a little bit more, is introduce a light bulb into the circuit. Just to try to learn a little bit more, I'm going to introduce a light bulb because we're going to talk about open circuits and short circuits here in just a second. So what I'd like to do is, if I put the light bulb here, it'll work, but I don't want to burn it out. So what I'll do is I will put the resistor in what we call series with the light bulb. I'm going to do a whole lesson on series and parallel circuits, but for right now, just know that when two or more elements are in series, it just means they're in a straight line path in the circuit diagram or in the circuit in the circuit. So what I'll do is send the electricity through the resistor, but then it immediately goes into the light bulb. So I just have a little coil of wire here going into the light bulb, and then it's going to go to the other side right here. And then you can see the light bulb is illuminated. Now, if I increase the voltage a little bit more, the light bulb can get brighter, and as I decrease the voltage, the light bulb can get dimmer. That's the whole point here. But I want you to notice something, and what I really wanted you to notice the current flowing through this circuit is 0.335 amps, right? But if I take the light bulb out, so it's no longer there, and I just have it go through the resistor by itself, this is what we had before, the current is a little bit higher, 0.470. And actually, it was a little bit higher before. I told you these things can change. This thing is actually getting kind of hot right now. But I mostly wanted you to see or know that there is a difference in the current when I introduce the light bulb. Why is that? Shouldn't everything be governed by Ohm's law? Let me disconnect this, and let's draw another circuit diagram, just so we can understand a little bit more, right? If I have a light bulb in that situation, here is the voltage source. It's still 5 volts. I still had the resistor, which was in this case 10 ohms, and I still had the other side of the circuit. But what I did is I inserted a light bulb here. Now there's a couple of symbols for a light bulb. You might see a light bulb written as like a little filament inside like that. You might also see a light bulb written with a little X through like this. It depends on what diagram you're looking at. It's just a symbol, so whatever you want to use. I'm just going to put an X in here, there. Now, if you were to calculate the amount of current flowing through the circuit, you could not use 10 ohms. I is equal to V over R. You couldn't just use the 10 ohms. Why? Because as the electricity goes around through the circuit, it's going through the resistor, but it's also going through this light bulb. And I never told you what the resistance of that light bulb is. Everything in the real world has resistance. In fact, light bulbs in particular have a fair amount of resistance because that's what makes them light up. The friction of the electrons going through causes it to get hot and causes it to glow. So just to say that we dotted the I's and crossed the T's, let's put this here and let's measure the resistance of this light bulb. So I'm just going to put my 2 probes right on top here, and I'm just going to push as hard as I can within reason, and we'll see that over there on the display, it's just a little bit less than 1 ohm, 0.7 ohms. But don't forget that whenever I had the circuit going, the bulk of the resistance was only 10 ohms, so adding another 0.7 ohms is just a little bit less than adding a tenth or 10%. So by putting this light bulb into the circuit, I changed the resistance of the circuit by almost 10%, and that's going to affect the electric current. It's going to cause the electric current to be reduced. So whenever I hook this up like this, and I get 0.470, and then I hook it up like this, I expect to get something less because the total resistance of the circuit that is in series together has now gone up, so my current is going down in accordance with Ohm's law. So if I were to use Ohm's law to calculate a value here, I would be dividing by, essentially I have to add these together, it'd be like 10.7 or 10.8 is what I would be dividing by. But let's look at one more thing, and let's just convince ourselves of one more thing here. Now check it out, we have only a single resistor, this light bulb is not involved at all, and the current flow is 0.470. If you remember, it was actually higher earlier when we did it. It was almost very, very close to 0.5. The only difference is, notice this extra alligator clip I put in there, I left it in there. If we remove that and put this back on, notice that the current is back up to 0.5, almost exactly 0.5 amps. Let me do that one more time. If I just insert this alligator clip, here, that it's not 0.5 anymore, it's much less. What's the difference? Well, there's physical resistance in the wire here, but there's also contact resistance from where the clamps are clamping on. Anytime you have a interface between metals in a circuit, you need to make sure that the contact resistance is as low as you can. Usually in real circuits, we solder them together to make a very low contact resistance. We never use clips like this, and you can see why. Because just the act of putting a clip in there is basically changing the circuit, introducing resistance. But still, the point stands, since I leave everything the same, 0.470 here, and then whenever I introduce the light bulb in, of course that's adding even more resistance, and so you get less current out of it. So that was the main point of that. Now what I'd like to do is really take up a deeper dive into what exactly is electric current. So we have to do a little bit of lecturing here. So let me go over, and I guess I'll draw it right here. All right? The concept of electric current, we talk about amperes. 1 amp, right, is exactly equal to the following: 1 coulomb per second. And the way you see this abbreviated a lot is 1 coulomb per second. Now, coulomb is a unit that you don't use much unless you're in a physics class. So we have to do a little bit of physics here, just so you understand. I mean, we're not going to really use coulombs all that much when designing circuits, but I want you to know what the concept of a circuit is, or what the concept of electric current is. So, first of all, I told you a long time ago that the concept of current was the flow. I use the word flow because flow means some material object is moving. That's what flow is. And I talked to you about a river or a stream. The water moving is the flow. And so we talked about electric current being the flow of electric charges. And now that I'm telling you that the unit of an ampere, which we know is electric current, is what we call a coulomb per second. So you don't know what a coulomb is yet, or I haven't talked about it, but this is a flow of charges, coulombs per second. A unit of coulomb is related to the unit of a charge. And when you say that many coulombs per second, the higher number of amps you have, 1 amp is 1 coulomb per second, 2 amps is 2 coulombs per second, 3 amps is 3 coulombs per second, and so on. The higher number of coulombs per second is literally the number of charged electrons moving past a point every second. So it's literally the flow of electrons. That's why when I introduce this stuff, I tell you The current is what is flowing. The voltage doesn't flow. It's just the push. It's the amount of push I'm giving, like the pressure pushing into a hose to get the water to flow. But the flow itself is the same as the current here. That is coulombs per second, flow of charges. Now let's reach back into our memories of chemistry or physics or whenever you took this, and I'll remind you that one electron, the charge on an electron, is approximately equal to, that's what the squiggly equals, 1.602 times 10 to the negative 19 coulombs. I'll just put COU, and I'll put a C in parentheses so you can remind yourself of that. So when you look in a chemistry book or a physics book, in the front cover, it'll tell you the charge on a single electron is 1.602. Now, the approximately means there's lots of digits after here for more and more precise measurements. But it's basically 10 to the negative 19. If you remember scientific notation, the exponent with a negative, it means you move the decimal 19 places to the left. So one electron is a really, really, really small amount of coulombs, right? It's a tiny, tiny charge because electrons are tiny. I mean, they're incredibly tiny. They have a very, very tiny charge. But we know that one of these coulombs flowing by per second is what we call an ampere. And we also know that a tiny amount of these coulombs is the same thing as an electron. So let's do some what we call unit conversion or dimensional analysis, and we'll understand where all this stuff is coming from. Let's go back to the concept of 1 amp, which is 1 coulomb per second. And we'll do a little dimensional analysis. We learned that 1 electron charge is equal to this many coulombs. So I'm going to put it like this. I'm going to say that 1 electron charge, or 1 electron, has a charge of 1.602 times 10 to the negative 19 coulombs. And I put it on the bottom like that instead of on the top so that the coulombs would cancel. So if I take the 1, and this is a conversion factor. It's telling you that 1 object, which we call an electron, has a charge of this in terms of coulombs, right? But we know that 1 coulomb per second is what we call an ampere. And so what I'm going to do is arrange it. I'm going to take 1 times 1 divided by this number. And when you do this division, because we started with 1 coulomb per second, which is the same thing as 1 amp, what we're saying is that once you do this division, you're left with the unit of electrons flowing past a point per second, then it's equal to 6.241 times 10 to the positive 18 electrons flowing by per second. So remember, from the beginning of the discussion, I told you, current was the flow. I said, hey, trust me, it's the flow of charges per second in the circuit. And this is the connection point that allows you to understand that. Because I'm telling you that an ampere, 1 amp that you're seeing on the meter is equal to what we call 1 coulomb per second. And then I'm telling you a tiny, tiny, tiny little amount of coulombs is just 1 electron is a tiny fraction of a coulomb. And when you put those two pieces of information together and the units cancel out, what you're saying is that 1 amp, which is a coulomb per second, is equal to this many electrons flowing by per second. And it's an enormous amount of electrons flowing by every second. So when I connect this thing over here, right, like I'll just do right now, and it's telling me 0.470 amps are flowing out of this thing, what it is, since it's pretty close to about a half, it's about a half of this number. So 3 point something times 10 to the 18 electrons every single second flowing through this wire. If you slice the cross-section of this wire, cross-section is like a circle, right? That's how many electrons flowing past per second on average there are. That is the definition of what an ampere actually is. And so we don't use the charge flow per second too much unless you're doing a lot of physics experiments or things, but I still want you to know where these units come from. An ampere is a coulomb per second. We know how many coulombs are in an electron, so an ampere is a lot of electrons flowing by every single second in an electric circuit. All right, now that we understand and reviewed voltage, current, resistance, now that we've kind of reviewed Ohm's law, now that we talked about the concept of current and a deeper dive into what electric current is, it's electrons flowing by a point every second, that's what it is. Now we're going to talk about the concept of an open circuit and a short circuit. So what I want to do is connect this, and I'll try to make the light bulb, I think, a little bit brighter. So I'm going to go a little bit above. I'll go up to right around there, just so we can see it a little more clearly. So here is a light bulb.
right? And we have a 10 ohm resistor in series with this light bulb here. And we can see that we have a voltage applied across the whole thing, and this is the amount of current. Now we know what current is. It's how many electrons per second, according to this conversion factor, are flowing through this circuit, essentially. Now what we want to do is talk about an open circuit and a short circuit. If we say we have an open circuit, it just means that the circuit has come disconnected somehow and it's now open. In this case, there's only one path for the electricity to go through. So an open circuit would be, for instance, let's say this is in an aircraft and it's vibrating all the time. It's shaking constantly in a rocket or an aircraft. Eventually this thing comes disconnected. You know, it might sit like this, you know, kind of like shake, like oscillating for a long, long time, and eventually it gets the vibrations are so much, eventually it just gets disconnected. This is called an open circuit. Notice at the moment that I opened the circuit, the current went from whatever value it had to 0. The current went to 0. Why? Because in order for current to occur, you have to have a closed path to go back to the power supply. The voltage doesn't change. Why? Because the voltage doesn't move. The voltage is the push. There is still pushing happening across the terminals of the circuit, just like there can be pressure in a garden hose. But if the spigot is closed, or I let go of the handle and no water can flow, there's still pressure in the hose. You can think of pressure in a balloon or something. You blow up a balloon, there's pressure in that balloon, but there's no flow coming out of the balloon. So nothing's going to happen, but I can still have pressure, I can still have voltage with no current flow. That's why there can be voltage here, but no current. As soon as I connect the circuit there, then the push begins to be able to push, the voltage can push the charges around the circuit, and so the thing begins to operate. Now we're at a steady state of this voltage-current relationship along with the power listed at the bottom. We'll talk about power later. But you hit some turbulence in an airplane and suddenly the thing comes disconnected. The current's bouncing all over the place because it's intermittently connected or not, and then it just becomes disconnected, current goes to 0. That's called an open circuit. If you ever see an open circuit, something's come disconnected. Usually, not always, depends on the circuit, usually it means the current goes down if you have a disconnection. But it also depends on the design of the circuit, so I don't want to make a blanket statement like that. So, if that was an open circuit, can you guess what a short circuit is? A short circuit is nothing has opened up the circuit path. Instead, in a short circuit, a situation has happened where we're basically bypassing the other circuit element. I think I want to draw a quick diagram of a short circuit before we go any farther. I think it'll make it a lot easier to understand as I show you what it is. Let's draw our circuit again. 5 volts, right? Here is our resistor, and then right here is our light bulb. I'll put a little X for the light bulb, and then we go back around. This is 10 ohms, and this has whatever resistance it has. I'm not going to write down what resistance it is. Now, before anything happens, the current is flowing out here from the positive terminal back around. Now again, the electrons really are going the other way, but we're writing down the positive current flow because in engineering, that's all we ever write down. The positive current flow, which is always the opposite direction of the electron flow. I'll talk more about it in just a minute. All right, everything's fine. But then what happens if a strand of this wire over here, like all of these wires are braided and stranded, right? Let's say due to vibrations in a rocket, a strand of that wire gets disconnected. And it connects up here to down here at the bottom of the circuit. What is going to happen to this current, right? The current is going to flow through the resistor, but when it gets to this junction point, it's going to branch off. Some of it will attempt to go this way, but some of it will go this way. And the way it's going to work out is it's going to take the path of least resistance. That's always going to be the case in electric circuits. The current is going to branch, but because this is just a wire connecting it and there's effectively no resistance at all here, 100% of the current is going to flow through here and it's going to bypass and not even go through the light bulb at all. In other words, it's going to short circuit the light bulb. So a short circuit that's why it's called a short circuit. You've kind of like cut the circuit shorter than it was and sort of made it stop and not go all the way through the load. Instead, it short circuits and circumvents the load and goes through here. So if you actually had a short circuit there, the current would then go this direction, and basically none of it would go over here. Now, if the short circuit had a resistance to it, then what would happen is some of the current would go this way and some would go this way, and it would depend on the value of the resistance over here, because you can mathematically calculate if it were not exactly a perfect short circuit, what would happen if there was a resistor in here. But in this case, if it's just a wire connecting it has no resistance, all of the current will flow through the short circuit. So if all of the current goes here, what's going to happen to the light bulb? It's going to go off. It's going to go get dim, right? Let's see if that's what happens. We have a nice light bulb here. I'm going to try to arrange this in a similar way. I guess I'll just leave it the way it was over here. And if I connect a wire here, this is just a stray wire. If I connect it here, nothing's going to happen at all because it's just like two parallel paths the electricity can go. But if I connect it here, all the electricity is going to go through the white wire and completely bypass the load. And let's see what happens when I touch it. Even when I touch it, the light bulb goes off. Why? Because the electricity is going through that wire. I'll touch it again. Electricity is going through the wire and none of it's going through the red wire anymore. Why? Because electricity wants to flow through the least path of resistance. It's just like a river. It wants to go through the path of least resistance. If I present a zero resistance path, it's going to go there and bypass the light bulb. Notice the current is starting here, but what's happening whenever I do the short circuit? The current increases almost to 0.6 amps. Why does the current go up? Because remember, we drew a picture over here, and we said this circuit really looks like this. It's a resistor with a light bulb. But if I actually short circuit the light bulb, then it's like the light bulb isn't even there because no current is going through it at all. So notice that in the beginning, it was like 10 ohms, and this is like, let's say 1 more ohm. So like 11 ohms total, right? But then if I short circuit this is like not even there. Now the resistance in the circuit is lower, and that's why the current goes up. I'm going to say that again. If I short circuit the load, then the current's not going through it, and the resistance of the circuit, it's like this part of the circuit's not even there. All of the circuit is here. Only 10 ohms means you get higher current. So every time I do this short circuit, look over here, the current goes up and the power delivered goes up because I have a less resistance in the circuit. Yes, the light bulb is still there, but because no current's going through it, it's effectively like it's not there at all. And a short circuit, bottom line, is a short circuit can lead to very high current surges. It can lead to a current spike. And when a current spikes, it can cause a fire. So we have circuit breakers and we have fuses to detect spikes in current, which can be caused by short circuits. And it can a short circuit or a fuse will open up and stop the circuit from happening. So if I had a fuse in here, it would detect the high current and it would open up. It would literally break open and stop the flow of electricity. That is what the circuit breakers are doing on your home, outside your house, or even in your car, or if you fly airplanes. There's fuses and circuit breakers inside of airplanes for the same exact job. All right, so we want to conclude the lesson with a little bit more of the theory behind the current flow itself. I'm not going to say that you would probably use this in everyday circuit analysis, but it's very useful for you to understand the basics here. So I am going to cover it. It's only going to take a few minutes. I promise it's easy to understand. So what I want to do is write down a more detailed equation to what the electric current is. And we can say that the electric current flowing in a wire I is equal to the following: N times A times V times Q. Now there's a lot of letters here. Let's explain what they all are. I promise they're not difficult to understand. Okay, the N is just like from chemistry, PV equals nRT. It's very similar to the N there. It is the number of charge carriers, in other words, number of electrons, per volume. In other words, it's the density of electrons. For a wire, we're going to have a high density of electrons because there's a lot of free electrons. In plastic, there's not very many electrons. Of course, the number of free electrons is going to impact how much current can flow. So the number of electrons in terms of density in a substance is going to influence the current that can flow. Makes sense. So that's the first variable. The second variable is the area. And what I mean by that is the cross-sectional area. Every wire can be thought of as like a little cylinder, right? And so there's a cross-sectional area here, there that you can talk about. So the thicker the wire is going to have a different cross-sectional area. That's all that is. Let's call what we call the drift velocity of the electrons. Now this is really where the rubber meets the road. It's basically how fast the electrons are moving through the wire, right? Because that's going to affect the current, as you might guess. How fast those electrons are moving through the wire in terms of their aggregate drift. I'm going to talk a lot more about that in just a second. Is going to influence the current. And then this Q here is what is the charge on each carrier. Right? In this case, an electron has a charge of -1, so Q is -1, and so that's going to impact the current. But if it was some ions in a plasma where the charge was like +3 for every carrier, then you would have like a different charge for every carrier. But for electrons, basically N is how many electrons per unit volume there is in the material. A is the cross-sectional area of the wire, or whatever. V is how fast, as a group, or as in terms of an aggregate flow from one end to the other, what we call the drift velocity of the electrons. And this is what is the charge on each electron, essentially. Now, what I'd like to do is explain where this comes from, because it's very easy to understand, right? You got to think of a wire. You got to think of charges flowing through a wire. Let's do some units. N is the number of charge carriers per unit volume. The way you write that down is number of carriers per unit volume. So you put per unit volume. That means per cubic meters. That's what N is. But then what we're going to do is we're going to multiply that by some cross-sectional area of a wire. But the unit of area is in square meters, right there. That's what we're multiplying right here. And then the velocity of the electrons as a group, as a total group, as an aggregate, is meters per second. So the unit of velocity is meters per second, right? And then Q is the charge on each carrier. But the charge on each carrier is coulomb per carrier. I mean, that's what it is, right? It's how many coulombs exist on one electron. Now, notice what's going on here. When you multiply all these things together, what you have is you have the carriers canceling with the carriers, and the meter squared times the meter is going to give you meters cubed, and together that's going to cancel with the meter cubed on the bottom. So what is going to be left over is going to be coulomb per second. Coulomb per second, which is exactly what I already told you the current was. I said the current is an ampere, which is called coulomb per second. 1 ampere is called 1 coulomb per second. And this is the nitty-gritty details of why it's equal to a coulomb per second. Because if you pretend this marker is a wire, and it's full of electrons, the more electrons you have, the more conduction you might think you have, right? That makes sense. Now, what you have is a density of electrons, right? As you take a cross-sectional area in square meters here and multiply it by meters per second, it's like zooming in on this and looking at a tiny little volume of this marker. Because when you look at the cross-section and multiply by a distance unit, it's like giving you a tiny little volume element. But when you take that volume element, multiply times this, what you get is a number of carriers, a number of electrons in a tiny volume element passing through a position every second. But every carrier that you got, so this is when you do this multiplication, it's a total number of carriers in a tiny volume element, right? But every carrier, we know how many coulombs it is. And so when we do that multiplication, the carriers drop away and we get coulombs passing through a point per second, right? So I'm showing you by the units that these particular variables multiplied together give us the correct units. Now let's see if it makes sense. If I increase the number of electrons per cubic meter, I should get higher current. Okay, it makes sense. If I increase the surface area, the cross-sectional area, should I increase the current? Actually, yes, you should. If I have a wire this big around versus a wire this big around, it's going to be easier to move current through a very large cross-sectional area, right? We're talking about DC analysis here. Things change a little bit when you have AC. We'll talk about AC later. But for DC analysis, if you have a very fat, stubby wire, you have a lot more electrons to move, so the current possibility for electric current should be higher. Very thin wire. It's just like blowing through a soda straw. It's very difficult to get a lot of flow through a tiny soda straw. Thin wires, not so easy to get current. So more electrons per volume, more current. Bigger cross-section of the wire, more current. Higher the velocity of the electrons moving, more current. And however, higher the number of charges on each electron, more current. Now, which of these can we actually control by our circuit? Which of these can we actually control with our circuit? We cannot really control the number of electrons per volume unless we're just choosing a different material for our wire. So let's just say we can't control it because we always use copper because it's cheap. Of course, there's other wires and other metals that have better or worse resistance, okay? But let's just say that we're not going to change the materials. That's the only way you can affect this, right? But we can change the cross-sectional area. We would want to use fat, thicker wires when we can, right? And this charge we can't change. This is the charge on an electron. We can't change that at all. So all we can really change is the thickness of the wire and how fast the electrons move through the wire. How are we indirectly controlling how fast the electrons move through the wire? We're changing the voltage. The voltage is the push. Remember, it comes full circle. The voltage is the push. More push means the electrons move faster, or can move faster through the wire, giving us more of an electric current. All right, so that's how you get more current. You get it by, you want as fat of a wire as you can get, and you want to push those electrons as much as you can. That's going to give you the most current, assuming you keep everything else constant. Very thin wire, like small soda straws, it's not going to be easy to get a very high current. Fat, thicker wires within reason, you can do a little better with those. All right, now the last thing I want to talk about is a little more discussion, and we'll wrap the whole thing up, about the hole current versus the electron current, and we're also going to touch a little more into this concept of, I kind of glossed over it, I said the electrons are moving with a drift velocity, so I want to talk a little bit more about that. All right, now I drew a picture of this in the last lesson, so this is going to be a very quick version, but in a wire you have some positive nucleus and some electrons surrounding it. Of course, the nucleus has more than one single positive charge, but I'm just drawing it like this for simplicity. Right next to it is another nucleus with another free electron. It's not really a free electron, but a very weakly bound electron, and another one right next door, and another one right next door. In copper, there's a lot of these little free electrons here. So what I'll do is I'll encase this thing in a wire with some cross-sectional area, right? That's the cross-sectional area that we had from here. And the thicker the cross-sectional area, the more of these atoms and electrons are there. And what we'll do is we'll connect it to an external circuit. We'll connect it over here to a voltage source like this, and we'll put a minus sign and a plus sign right here. All right? Now what this means is that because the negative sign on the power source is right here, what it really means is that there's electrons moving out this direction. But again, we don't ever write electron current. We always write the hole current, which is going the other way. So what I'll do is I guess I'll do it in pink here. I'll write the hole current, which we call hole current. And what we actually use the letter I. That's the current that we're always calculating. It's coming out of the positive terminal, going through, and then back around. It's always opposite of the electron current. Now again, we know that there is no such thing as hole current. We know that. So I get emails like, don't you know it's not real? Who cares? It's a model of reality. We know the electrons are going the other way. But mathematically, it's simpler to talk about the hole current going the other way. Why? Because what's really going on here is when a voltage is applied, this voltage basically produces an electric force on these electrons. And this electron, what color do I want to use? This electron is going to attempt to well, you can think of it like this. If this is positive, it's going to attempt to attract this electron out. But once there's an empty vacancy, or you might say a hole there, this electron will be then attracted to that positive nucleus. And now there's a hole right here. And this electron will be attracted this direction to fill the vacancy. Now there's a hole right here. And then there's a vacancy that's going to be attempted to be filled right here, and so on. You see the word hole I'm using? This is a positive side of the terminal. This electron will be instantly sucked off, and now there's a hole there. Then it backfills. There's a hole there. Then it backfills. There's a hole there. Then it backfills all the way around. And so what happens is, even though we know the electrons are going this way, there's almost like a positive hole moving the other way. It's like originally there was a hole here, but then when this one backfilled, the positive hole was here. A hole, in terms of circuits, is the lack of an electron. When we talk about a hole, you can replace it in your mind with the lack of an electron vacancy. So we could call it vacancy current if you want to, instead of hole current. So there's a vacancy here, but when this one goes here, there's a vacancy here. But when this one goes here, there's vacancy here. But when this one goes here, there's vacancy here. So the vacancy hops from charge to charge this way. That's what we call the hole current. That's why it's opposite of the electric current, because it's literally bookkeeping the vacancies in electrons going the opposite way from the electron flow. That's what we talk about when we talk about electric current. So hole current goes this way, electric current goes this way. Now the last thing I'm going to talk about is this velocity in terms of the electric current right here. It's frequently said that when the electricity is turned on in a circuit, it's the speed of light. You know, it travels at the speed of light through the wire, and I've even said that before. It's a little sloppy to say electricity moves at the speed of light, but it's also not totally wrong either. Let me explain. What's really going on is the electrons are hopping, but what's happening is they're colliding with other atoms, they're ricocheting, bouncing. You got to imagine, I only drew 4 atoms here, but there's trillions of atoms. And as this electron moves, it might collide with another electron, might go backwards for a second, bounce this way, go up, and then it might hit another vacancy, but down here, and then up here, and then backwards, and here. So these electrons, as they move, they're colliding, and they're going backwards, ricocheting, going the other way. Eventually, they do go in the direction that you expect them to go, but it's through a lot of intermediate collisions that they eventually make their way in the direction you expect them to go. It's not as simple as, oh, they just go this way. They're colliding constantly. The microscopic scale, everything's vibrating and constantly colliding all the time. So actually, what we call the drift velocity of the electrons in a circuit is only about 1 millimeter per second. Or even down to 1/10 of a millimeter per second. So if you track a single electron and you say, okay, I start from here, and then 1 minute later I see where it is, and it's over here, it might only have gone 1 or a millimeter or 1/10 of a millimeter in a second. That is not anywhere close to the speed of light. So why do we say electricity goes near the speed of light? Here's why. Because the individual electrons are colliding and going crazy. So if you track one electron, it's not moving very fast. But as soon as this electron goes here, the next one immediately gets pushed the other way, and the other one gets pushed the other way. So there's sort of a chain reaction effect here. When one electron gets here, it kicks the next one out, immediately vacates its shell. Or if you want to think of the other way, once this one gets sucked out over here, there's a vacancy that's immediately pulling this one over, and then another vacancy that's immediately pulling it over. There's a chain reaction, so it's like, as soon as one comes out, whoom, there's like a chain reaction where everything tries to move. So one single electron might collide and go backwards and forward and not really do much and meander. But when we say electricity travels close to the speed of light, what we're saying is when we turn the voltage on, the current is flowing almost instantaneously, almost near the speed of light, because the chain reaction of when this one comes out to this one moving over here, that is almost at the speed of light. Let me say that again. The chain reaction, when this one gets sucked out, the time delay between this one getting sucked out to this one being sucked over here, like all the way at the other end of the wire, is almost instantaneous. Because as soon as this is gone, this one starts to move. Even though there's collisions, the chain reaction of movement is almost instantaneously. Why? Because the electric forces, the force between the electrons, is millions and millions and millions of times stronger than gravity. We don't think of gravity as being a weak force, but the gravity holding me down is very weak compared to electric forces. As soon as there's a vacancy in a hole, it's going to suck in another electron because that electric force is so strong, and that chain reaction rippling through the wire, that chain reaction happens nearly at the speed of light. And so we turn the circuit on, it begins to operate very soon after we start near the speed of light. Even though each individual electrons might take a long time to go all the way around, the chain reaction is what matters in circuits. That's why we say it occurs close to the speed of light. All right, that is about all I wanted to say here. We talked about Ohm's law. We talked about what exactly governs the concept of current. We talked about the units of current. We talked about an ampere being a coulomb per second. Then we were diving into the concept of the variables that affect current. We built a couple of circuits. We talked about open circuits, short circuits, the danger involved, especially with short circuits. Hopefully this practical angle gives you some encouragement to learn more. And so I'd like you to drop me a line, let me know what you think. Follow me on to the next one.
Learn anything at mathandscience.com.